In the third part, we are going to learn what it means for two statements or two propositions to be the same and the same. In this case, it we mean they are equivalents. They are kind of equal, but not equal as an equation where values are the same. But the logical or the logic, the truth values are identical in all cases. So this is what we mean when we say two statements are the same. If you go back to the example about cars, remember that I mentioned a little bit that if you if you consider the truth value of P and Q, that's gonna give you the same table, the same statement as not P, then not Q. And the question is what it means by is two to be the same. Let me know that one sentence or one statement is the same as the other. And the answer is we simply look at the truth table. If you construct a truth table for both statements, both compound statements, and they all truth values match on each row, then we say that they are equivalent. And again, they are not the same. Just like I love math and I hate brain. They had the same truth value, but they in no means the same statements. Let's still an example here. We start from we start from example right now. No. So let's this one asks you to create a truth value for not P, not P, a double not, and then find a position that is equivalent to it. So usually if in other classes or in visual textbook, you are given two statements and you are asked to compare them. But here I asked you to do one and then I asked you to find another. Let's go through everything else you have so far and then you can match them. Just like when you do the jigsaw puzzle, you have two statements and you see if they match. But let's start from this one. There's only one. There's only one proposition P. It can be either true or false. Put an indication. And that's the inner part. We start from inside parentheses first. Then we flip truth value that becomes false and true. And then in the next step we do that again. We flip. We just flip it one more time. So false becomes true. True becomes false. And if you simply take a look at this table long enough, you will notice that actually this brings you back to the original column. What it means by what this means is that P is equivalent to not P. If you construct a truth table for both these proportions, you're gonna get the same truth values for each row. Like this row match, this row match, but they are the same. And again, this is what we use in English, like in language as well, because if I don't want to not do it, it means I want to do it. Something like that. Let's try next. So we're going to a tutorial for P or false and find a proposition that is equivalent to it. And maybe this is a new one. Let's stop for a moment. What it means will be P or false. Because P is a proposition, it can be true or false. We don't know it yet. That's why we have to list all the possible combinations. But the latter part is false. It means it's a statement that we know to be false for sure. For instance, this statement might be equivalent to I have a pet or am a millionaire. Millionaire. So there are two statements. Usually you think of it as P and Q. But in this case, you can maybe somewhat. You can kind of see that. Oh, actually, this is false. You didn't have to prove that. And so this statement will be equivalent to something that we have to find the truth value. Something that is clearly false or clearly true. In this case, it's clearly false. We use false. So if I say this sentence, would you say that my statement is true or false? Like this whole statement. Even though it seems like something is false, it doesn't mean that the whole thing is false. We have to consider the proposition or consider the conjunction. So in this case, we have to the table. There's only one proposition, so just P. We have that. And we are looking for P or false. If P is true, then we have false or false. If P is false, if P is true, then we have true or false. If P is false, then we have false or false. The letter is fixed. The formula can be. Again, go to the table of or true and false. So this means that these statements, P or false, give you the result of true, when P is true and false, then P is false. And again, you have to go look at tables and see which one is matched. And is it not difficult to see that, oh, this is actually the same. P on the left, P or false on the right are actually the same rows. That means we can include that P and P or false. That is equivalent. They give you the same root value. In one way, if you do the math, then this is what you get. In another way, like if you have a statement and you know for sure that the latter part of the or is false, then it's kind of like you can ignore that. This is implying that if you know that one statement is false, and you combine them with the or operation, that means you can get rid of the f. And if you know the algebra, this is equivalent to if you have P plus 0, you get a P. It's somewhat equivalent. Just in case you know that. Adding 0, it doesn't change the value. Likewise, operating a statement with the false statement doesn't give any fact about itself. So there's P and PRF equivalent. Right, then we have some equivalent statement. And let me make a remark. Maybe I should make it inside that. Is that you done? No need to memorize. But what is important about this statement is not about getting everything correct every time you are asked. Life is not just a series of quiz. Right? The important thing about this statement is that can you read that and see why each statement is true? Okay, so let's go over together. For instance, the third statement we just did, right? P or false is P is equivalent to P. What it means is that if you know that something is false already, and then you operate that with another statement, with the or statement with another value, then this doesn't matter. The whole thing relies on the fact that it's true. If you think about maybe like a game show, let's say it's you and your friend, or you both to qualify for the next round, then either you or your friend must qualify or pass the test. Right? In this might be the statement that says, oh, you know that your friend fails already. That means The fate of you and your friend relies on you. If your friend fails the test already, then the fate of both of you is the same as the fate of yourself. So that's what this means. If one of them fails already. So that's what the third statement means. And yeah, but what about the first one? PR3 is true is true. What it means is that if you combine a statement with a true statement, then again it's a matter whether the first statement is true or not. The result is true anyway. And again, similarly, if you think about the same competition, you want you or your friend to qualify. If your friend qualifies already, then you don't matter because you will qualify anyway. You require at least one of you to qualify, and you know, oh, your friend qualifies. That means you are free to do whatever you want. If you fail, you both gonna qualify. If you succeed, you both qualify. Or qualify? I don't know if that's a word or not. So that's what we mean, both by math logic and by language counterpart. And 2 and 4 are similar. Think about it. What do you mean when we combine that with the and statement? For instance, if you want, if instead, if you take another competition or something, you both need to qualify to pass to the next round. If you know that your friend fails already, then again, it doesn't matter what you do. You both gonna fail. For instance, that's the first set. And the second set is more interesting because this is actually what we use in life, but sometimes you don't notice it. Let's start from the first one. This is so complicated at glance. What we have here is we have P or Q, and then we put the negation in front to flip the truth values. We are claiming that this is the same as not P and not Q. It's slightly more complicated, so maybe the first step is to see if you can translate that into a sentence and see whether they are true or not. For instance, if let's say if you want to donate your blood, there are several conditions. The first step to be able to donate your blood, you need to be above 18 or have consent from your parents. 18 or your parents' consent. Have. Is it a verb? What's that the condition? So you need one of these to be true for you to be able to donate your blood. And the question is, like, on the left we have this part, right? But then we have to negate that. So you ask yourself, what it means for this whole sentence to be false? What it means for the or statement to be false or to have the different or have the opposite. Have the opposite truth value. You can't do that. You are not qualified to do that if you are not above 18 and notice that the condition becomes and no parents' consent. If you fail to to qualify to donate your blood, then you must fail both requirements at the same time. You must be below 18 and to have no consent to fail the test and to not be able to give blood. And if you think about it, this is what we think about that statement in terms of language, right? And then you use that statement to compare with what we have on the left hand, on the right hand side. And you can see right away that they match. You have to not be above 18, not P, and not Q, and have no consents. So again, this is actually the language part that corresponds to maths equations or the logical operations. So this is what we have for this one. Oh, and maybe make a note that it is not the same as when you distribute minus 2 term. We have minus a plus. This doesn't change, the plus doesn't change to something else. You can think of it this way, but you can think of it in terms of language. And what you mean for the or sentence to be false or to be negated. Two is also similar. You just flip that from or to n and n to or. And again, think about it for a second. What it means for a sentence to be, what the end sentence to be false. For it, when either of these statements or either of these requirements is true. So the end statement is false when either of these is true. Is false. So that's the explanation behind the second statement. And lastly, we have the if then, and this is what we talk about twice, about the that example and about the card example. That P then Q, that statement is equivalent to not P then not Q. We're gonna go back to the middle one for a moment. But for instance, for the statement, if a card is even, then is back is blue. And this is what we have. We claim that if you know this property, like we would know that this statement is the same or is the same true value with the statement that if the back is not blue, then the card is not even. The card, the number. Okay, then the card is not even. Once we know that fact, then we know that we have to check even card and check cards that is not blue. That's the third one. And interestingly, that you can see there's a middle part here that says actually like if then statement is equivalent to or statement. This is difficult to see, but if you take a look at the table, the or statement is true, and false. There is false in one position. If then statement likewise is also false in one position, which is in the middle. And this is kind of saying that there's a way to like kind of flip that to compare this to the other one, which is to add the not in front of P. And again, you can think of them as in English sentence, E then Q, and then think about the not P then Q, or not P or Q, when they are false, when they are true. So that's some logical equivalence when you compare that two different statements and see if they are the same. And then we can skip this part. Yeah, let's skip this. This actually is short. And lastly, we can reduce. Just like in math, like if you have P plus 0 equal to P, then you reduce the operation to a shorter one. Likewise, you can reduce operations just like equations in logical equivalence. If you know in the first place, like what are the legal operations? For instance, you are allowed to swap places. What happened in math? You're allowed, I mean, this is and it is a property that you can swap.
Numbers you add numbers together. And
Likewise, you can swap that logical statement. You can see this by either thinking about them in terms of English. You say I want lemonade or I want steak. I want steak or I want lemonade. They mean the same thing. The sequence, the order doesn't matter. And also that doesn't matter. You can construct the truth table and see that, oh, actually we have the same results. Something is less obvious, like for instance, you can have P or P and Q. Actually,
Q and R is
equivalent to P or Q and P or R. Which I'm not gonna go over. I mean, this is true, but if I go over this, it's 30. But just to show you know, sometimes you can distribute logical statement. That's how you distribute numbers. If you know how to do that. Let me give one short example here. So we have there's a statement here, like P, then P or Q. One way to determine the truth value is to use the truth table. When you construct a table, let me do that real quick. PQ, you have true, false, true, and false. You start from P or Q. It gives you true, and false. Only one case when it's false. And if you have
combine that
with
too
small,
with
if then,
so you're
looking at the first one
and the third one.
Like P, true then true, gives you true, then true, gives you true, false then true, gives you true, false then false, that gives you true. Actually, this statement is always true. There's a word for this too, but we didn't go over that, which is the tautology. Some statement is always true, no matter what the truth value of each individual statements are. But anyway, yeah, suppose we know, oh, these are all true. Sorry, this should be P, not Q.
Or Q.
Okay, so there's one way to determine the truth value of this statement. Another way is to do the math. If you know, again, you are not supposed to. You don't need to.
You know that.
Suppose you know that. This is how you do it. Like first we say that, oh, P then Q. This is equivalent to not P, then the latter. Former then latter, not former. Not latter. We saw that above when you in property 3.3. This part. What next? The next thing is we do the this one we swap places. Like this is called.
I forget what it's called.
I know it's in Thai, but I don't know it's in English. Associative, I think this is associative property. If you have the same operations, then
you can switch the orders. And
then we know that not P or P is true.
It's true
or Q. Again, this is kind of a property. Or you can think of it this way: that if I say that I love math or I don't love math, then that sentence is kind of like meaningless, right? Because it's always true. I either love math
or don't. Or,
you know. even though I know it's the former, but this kind of statement by not P or P is always gonna be true.
And the statement
When it doesn't say anything, like one way or the other.
So
This is kind of
identity.
identity. Get that? And lastly, we saw above that three, true or anything is always true.
We
You know that true. It's true anyway in the first case, the latter doesn't matter. That's another way to deduce or to reduce or to transform one statement to. But again, let me make another note that you're not required to know this. Just, I don't know, a fun fact. This holds at some point. So that's the end of the third part.
Exercises. Want to do
Do that.